Welcome back to section 2 of chapter 2. In this section, we are going to get the first derivative rule, and this will make your lives much easier. You're probably pretty much done with the limit definition at this point after doing it for just a day. When I went through calculus, we did the limit definition for the full chapter, and then we started getting the rules. It seems a little bit excessive, but I mean, it's bad. So, the power rule is going to work when we have x to a power. So, and then we'll actually expand that to polynomials. So this is going to help out with all of those kinds of derivatives. We'll get to different types of derivatives later, like sines and cosines, exponential, things like that. Right now, we're just looking at x to a power. And so, first, let's look at what the power rule is and how we find it. It actually comes from the limit definition. So we're going to look at the derivation of the power rule. Now, chances are, in your work on section 1, you've already hypothesized this because it kind of shows up. If you were seeing patterns in the section 1 assignment, it's because you're seeing the power rule. So we're looking at the general case for f of x equals x to the n when n is a natural number. That means it's 1, 2, 3, 4, 5. X to the n when n is a positive whole number. So, and in your assignment, you're actually going to show that it works for cases where n is not a positive whole number, because it actually works for any n in the real numbers. But you have to show that all separately. So we're going to put this into the power, or into the limit definition. So f of x plus h minus f of x over h. And then the limit, we can plug in the x plus h to the n minus x to the n over h. Now here's where that binomial expansion comes in handy, because I know that x plus h to the n is going to be x to the n plus n times x to the n minus 1h plus this n2. This is not the, this isn't a fraction. This is the binomial coefficient, n choose 2, times n to the n minus 2 times h squared plus, and then we can follow the pattern all the way down to h to the n. However, and then minus x to the n on the end. All this stuff in the middle, these are all going to have a few h's in it. We're going to, just like we were doing yesterday, we're going to be able to factor out 1h. All of the rest of them will end up just going to 0. So all of this stuff in here is just going to go to 0. So we can combine our like terms. X to the n minus x to the n goes away. Now everything that's left has an h in it. So we can factor out the h. The h's cancel. Now we can substitute in for 0. When you substitute in for 0, this doesn't have an h anymore, but this has an h squared, h, all the way out to where it's only h's. So everything else other than just this one little first term is going to have an h in it. And so it all goes away. So you end up with f prime of x equals n times x to the negative 1. You started out with f of x equals x to the n. You end up with the derivative equals n times x to the 1. That is the power rule. The power rule, and this is purposefully larger here because this is a big thing. Generally, I tell people to write down all these rules that we're going to learn in the back of their math notes. If you just flip your notebook over, stick it on the back page. We'll be adding a bunch of stuff there. If you don't have to dig through your notes to find a rule, that makes it a lot easier. So that's just a pro tip. You don't have to do it, but it does make searching through notes easy. This one you're going to use so much you shouldn't need it. But when we get to some of the other rules, it'll be handy to have. So the power rule for f of x equals x to the n, f prime of x equals n times x to the n minus 1. To take the derivative of x to a power, we're going to move the power out front and then subtract 1 from that power. So if we were looking at, say, f of x equals x to the 6th, f prime of x will equal 6 x to the 5th. It's easy as that. It works when it's not just positive whole numbers too. We could have f of x equals x to the 3.7. F prime of x will equal 3.7 times x to the 2.7. Goes right like that. F of x equals 1 over x squared, which in this case I would write it as x to a power, because right now it's not written as x to a power. This is the same as x to the negative 2. So f prime of x equals negative 2 x to the n minus 1. Negative 2 minus 1 is negative 3. You think putting negative 1 is going to be a fairly common mistake in this case? Yes. In fact, how many of you thought negative 1 before I said anything? That's okay. You don't have to admit to it. How about f of x equals the square root of x? Writing square root as an exponent. It's going to be x to the 1/2. So f prime of x equals 1/2 x to the negative 1/2, which if you wanted to put it back as a root, let's say you were going to plug a number in and you can't think of how to do x to the negative 1/2 in your head, remember the negative, we'll put it in the denominator and the 1/2 will be a root. So this will be 1 over 2 root x. There's another one that people will make a common mistake on. F of x equals x to the 1/3. All right, take just a second, find the derivative. It uses the exact same process. 1/3 x. How many of you put to the negative 1/3? Yeah, what's 1/3 minus 1? Negative 2/3. Right? It's a common mistake. So when you're thinking about, just remember, you're always subtracting 1. So just taking a look at that, in that very brief span, we did 1, 2, 3, 4, 5 derivatives. These go fast. So that's power rule. Next, we're going to add properties of derivatives, because with these properties, we can expand it from just x to a power to encompass all polynomials. So what are some of these properties? And these properties are actually going to be fairly common sense with the ones that are here. There's a couple that you think should be here that aren't, and that's for a reason. But these ones usually make sense. So the derivative of a constant, if h of x equals c, a constant, the derivative equals 0. What does the graph of a constant look like? Graph of a constant, oh, that was almost bad. I almost drew it in blue, which wouldn't be bad except that it's on blue. It's the exact same color. It's a horizontal line. What is the derivative? The derivative slope. What's the slope of a horizontal line? The slope of a horizontal line is 0. So the derivative of a constant is always 0. Now, you're going to be messed with here, because you're going to have things like, what's the derivative of y equals 3 to the 7th? And people are going to go 7 times 3 to the 7 minus 1, so 7 times 3 to the 6. No, 3 to the 7th is a constant. x to the 7th is a power. 3 to the 7th is a constant, derivative 0. So be aware of that. A constant multiple, if you're multiplying by a number in front, then you're going to multiply the derivative by that number. What does this mean? Let's say we have y equals 3x squared. So to find the derivative of x squared, we're going to move the 2 out in front and subtract 1. So we'll have 2 times x to the 1. All it says is we're going to multiply the 2 times the 3. Y prime equals 6x. So whatever's in front of it when you're taking the derivative, you just multiply by that number. The sum rule and the difference rule means that you can add and subtract. If you're adding and subtracting functions, for instance, terms in a polynomial, you can add and subtract their derivatives. What this means is that we can have something like y equals 5x cubed plus 3x squared minus 7x plus 1. And then to find the derivative, we're going to find the derivative of each term individually. 5x cubed, we're going to move the 3 in front. 5 times 3 is 15. X squared plus 3x squared, move the 2 in front. 3 times 2 is 6x minus 7. Now remember, this is 7x to the 1. 1 times 7 is 7. X is 0. X is 0 equals 1. So that's just minus 7. And then plus 0, the constant, has a derivative of 0, so that just goes away. And so the slope of the minus 7x, if we graph negative 7x, that's just a line. Lines have a constant slope, negative 7. It's right there. So, but anyway, so the two sum and difference rules allow us to do stuff. It allows us to a polynomial, so we don't have to throw it into the difference or the definition. We can do each piece individually. So if we had another one, let's do y equals the cube root of x squared minus x to the, we'll go x to the pi, why not? Plus 1 over 3x. The first thing I would do in this case is rewrite stuff so it's x to a power. Y equals x to the 2/3 minus x to the pi. That's already a power. And pi is irrational. Who cares? Plus 1/3 x to the negative 1. Now we can find the derivative of each piece individually. Y equals, we have 2/3 x to the negative 1/3 minus pi x to the pi minus 1. People always say, what's pi minus 1? Pi minus 1 is pi minus 1. It's about 2.14, but just write it as pi minus 1. That's fine. Then plus or negative, because the negative 1 is going to come out, negative 1/3 x to the negative 2. There we go. That's the derivative. That's y prime. And so that's how we can use these properties of derivatives to find all these polynomials. Now again, there are some like 1 over x. That would be x to the negative 1. You're going to have to do that using the limit definition as well, just to show that you get the same thing. But that's a few right at the end, just to show those weird ones actually work. Other than that, it's polynomials. Um, be watching your subtraction. That's the thing that gets people. Um, make sure you're turning them into x to a power correctly. And other than that, it's super easy. It actually goes amazingly quick once you get a little bit of practice. And this is one of those things that we are going to be doing a ton of. This is kind of like the solving basic equations in Algebra 1. Pretty much everything we're going to do is going to involve this in some way. So that's what we're doing. We'll expand on this a little bit more tomorrow. And then later in the chapter, we'll do a little bit more. And then the next chapter, we'll learn about some different types of derivatives or derivatives of different types of functions. So keep working problems, keep asking questions, and as always, happy mathing.